So we're going to focus on what we call piecewise defined functions. What a piecewise defined function is we're taking a bunch of different functions and kind of mashing them together. And we're going to restrict what parts of the graph are going to be what functions. We're also going to look at some very basic what we call transformations. Shifting and reflecting of graphs are transformations of these functions. So we'll start with the piecewise. So when we're given a piecewise function, what we're doing is we're creating a list of rules or a list of functions. And then we're saying that this rule only applies within a specific domain. So with this function here, f of x is 3x plus 1 if x is less than or equal to 0. So it's saying that I have this line, just kind of draw a little graph, all right? I have this line of 3x plus 1, which would be, I don't know, something like this, okay? And it would go in both directions here and here. All right, that's 3x plus 1. But if I restrict the domain to say it has to be less than or equal to 0, then that means I'm not including any of that graph. I would get rid of that half. It stops at x equals 0. Then I have another graph. I have another line, x minus 4, which would be something, let me do that in a different color. Let's do it in green. I have x minus 4, and that would be something like this. That continues in both directions. But it doesn't go forever. It starts at 0. It starts where the other one left off. And so I would ignore this half of the line, and it would start here at x equals 0.
So that's, how do you know what it, like,
Less than is on the left, greater than is on the right. And so it's going to define the domain where that graph is going to be shown.
Does the or equal to?
So the or equal to versus the just the greater than?
Yeah.
So they're going to kind of pick up where they left off. I have to have a way to define which one is going to be my 0. That's what the or equal is. Remember when we did our our inequalities on a number line? And if I had 3 is less than, or x is, I don't know why I did 3. Okay, I had x is less than 3 on my number line, I would have an open circle and I would shade to the left. But if it was less than or equal to, I'd have a closed circle. We're going to do the same thing here. This one would have a closed circle because it's or equal to. This one's going to have an open circle. Yep. Okay. And we'll get to the graphing on the next one. We'll do the graph. Write our results. So we want to evaluate each of these functions, and we want to write a result in ordered pair. Okay. So we're looking at what these ordered pairs are going to be. So f of 2. What does that mean when I have f of 2? What does that 2 represent? The x value. So if x is 2, it wants to know what does my function evaluate, or what is the y value. Okay? So now I have f of 2, but I got 2 different rules. I'm not going to solve for both. I'm only going to pick one. Which one has 2 in its domain? The first rule or the second rule? The second one. Because it's x is greater than 0. So 2 is in that domain. So that's the rule that I'm going to use for f of 2, x minus 4. And so then I can evaluate f of 2 is going to be 2 minus 4. What is 2 minus 4? Negative 2. So when x is 2, y is negative 2. Again, we want to write an ordered pair. So my answer is 2, negative 2. When x is 2, y is negative 2. And then I could plot that point if I was trying to draw the graph. I could plot that point. If x is negative 4, which rule am I going to use? The first one or the second one? Because I want values less than or equal to 0. So I'm going to use my first rule because negative 4 is in that domain. X is less than or equal to 0. So I'm going to use 3x plus 1. So f of negative 4 is 3 times negative 4 plus 1. What is 3 times negative 4 plus 1? Negative 11. So my ordered pair is negative 4, negative 11. What about for f of 0? rule am I going to use for f of 0? Why the first one? It's got the or equal to. It's got the or equal to, and that's important because it's saying, hey, when x is 0, this is the rule that takes precedent. So I have 3x plus 1, so I can evaluate that function. What is f of 0? 3 times 0, there we go. Let's actually put that in there. What does that evaluate to? F of 0 equals, okay? So f of 0 equals 1, which means I have the ordered pair 0, 1. All right? Questions, comments, concerns so far? So bad? Look to see what rule is going to apply based on the x value that they're giving you. Plug it in, solve the equation. Now we're going to do the same thing for plotting points, but we're going to pick the x values that are going to make the most sense. Okay, so when we want to graph this, we're going to want to pick specific values that are going to allow us to graph the line where we want them graphed. So, two rule, similar, a little different. Okay, I got 3x minus 1, I've got x plus 3, and again, I've still set my domain to less than or equal to 0 and 0. It doesn't always have to be at 0, it could be any values we want. Picking 0 to 0. Okay? So we want to graph each piece separately, and I'm going to explain why I picked these specific values. You're going to have to get comfortable with picking your values of x, but I set these up to show you what you're looking for. One, you're going to want to include this critical value. Okay? Whenever you have a restriction on your domain and it's specifying something, you want to include that value for x because you need to know where your graph is either going to start or end. Where that line will start or end. You need that point. Now, what it looks like on the graph is going to be different for each rule because one of them is or equal to and one of them is not. That's going to be the difference between open circle and closed circle. Here I'm going to have a closed circle, and here we'll have an open circle. Okay? Because that's where it's going to change from one line to the other, but I can't have them both be closed because then I don't have a function anymore. It would fail the vertical line test there. So I'm picking values that are less than or equal to 0. I've got 0, I've got -1, I've got -2. I want values that will be on that line. 0, -1, -2. And then I can evaluate that function. So if x is 0, what does f of 0 end up being? -1. 3 times 0 minus 1 is -1. What about f of -1? 3 times -1 minus 1. -4. And f of -2. -7. So again, I have three ordered pairs. I've got 0, -1, -1, -4, and -2, -7. Those are three ordered pairs that I'm going to use to graph that first piece. Those are three ordered pairs I'm going to use to graph that first piece. And remember, this one's going to be a closed circle. That's our critical value. It's less than or equal to, so we have a closed circle. Now we need a graph on the other side. So again, I'm picking values greater than 0, like 1, 2, and 3. But I also need to include 0, but remember that it's going to be a open circle, whatever that value of 0 is, because it does not equal 0 for that line. That's on the other one. So if I have f of 1, what do I end up with? 4. And if I have f of 2, and f of 3, and f of 0. Okay? So I have these ordered pairs. 1, 4, 2, 5, 3, 6, and 0, 3 will have an open circle. A plot to draw my graph. Now remember, I'm going to have two different lines kind of mashed together, and there's going to be a jump in the middle, or there's going to be a change in the middle. All right? There's going to be a change in the middle. Okay? So my first piece was 0, -1, -1, -4, and -2, -7. And my second piece was it 1, 4, 2, 5, 3, 6. And then again, that open circle, at 0, 3. So let's start with that first piece. 0, negative 1. And then negative 1, negative 4. And then 2, 7. Okay? That's my first line. It starts at x equals 0 and then continues in this direction. If I didn't have that restriction, if it was just 3x minus 1, then my line would go forever in both directions. But that restriction, x is less than or equal to 0, says stop at 0. Do not go past 0. Stay with all the values that are less than 0 on the x-axis, so my line stops here. And then it's going to jump over to my second piece, because the second piece takes over after 0, going to the right. So I have 1, 4, goes up here. So 1, 2, 3, 4, and 2, 5, and 2, 6. So my line continues from there.
What about 0, 3?
Okay? The reason we have 0, 3 is because if I don't include this value, I'm leaving out all of these numbers between 0 and 1. I have a gap there, and I can't have a gap there because my domain doesn't have a gap. It changes functions at 0, but I still have all those values between 0 and 1. So that open circle says, hey, we're going all the way up to our x equals 0, but we need an open circle to say that it's not included on that line.
So you don't put the open 0 all the way down there?
I'm not going down here.
No, I'm talking on the other line.
This one is or equal to, right?
Yeah.
So this is a closed circle.
No, I'm talking on the other one.
Yeah.
See how you put the solid dots?
Yeah, these are points on the line. These are just regular points.
Okay, so those you don't make open.
Nope, just that change. Just where that changes. What am I going to do an open circle? Because that's what allows me to pass the vertical line test. And for it to stay a function is that when I put in 0, I have to know which function it goes to, which line it goes to. It's going to go to this one. For everything else, there's no overlap, so it's not an issue. And there's my piecewise graph. 2 lines and 1. 2 lines for the price of 1. Now again, it doesn't have to just be 2 rules. It could be 3 or 4 or 5. We're adding in some more rules. Okay? And so we have to see those domain restrictions. I have less than or equal to less than negative 2. I have between negative 2 and 1, and then I have greater than 1. So I have 3 rules, 3 domains, 3 lines. I also have 3 different types of functions. This first one's a constant function. That means no matter what x is, if it's less than negative 2, your output is negative 4. Then I have a linear function, 2x minus 1. Those are good old-fashioned straight lines that we're used to. I have x squared. What type of shape is an x squared? Parabola. That's that U shape. So when it transitions to x is greater than 1, we're not going to have a straight line anymore. We're going to start to have a curve. And so wherever we are in that curve is where it's going to take over. But we're going to have a curve. We're not going to have a straight line anymore. So you need to be aware of that when you're graphing it. It's not going to be a straight line once you get to here. Yes? Depends on where it starts, but yeah, you're only going to draw part of it.
Is that middle one? Is that
Yes. All right. So we're going to pick some values. We always want to include those critical values within our set. Okay. So for for f of x is negative 4, I need to include negative 2 because I need to know what it's going up to. And then I want to pick some other values that are less than negative 2. Give me some other values that are less than negative 2. Less than. Negative 3 and negative 4. Okay? Will any of these be an open circle?
No. Wait. No.
Yeah. This one will be. Nope, just that one point. Because that's where it's less than, not or equal to. Everything less than is fine. It's just the negative 2 is not part of that line, it's part of the other line. So I have to have the open circle here, knowing what I'm going up to, but not including. Now when I get to here, it's less than or equal to, and it's less than or equal to, so I don't have to have any open circles on this middle rule because it includes both of those points. But I need to include -2, and I need to include 1. And then I could pick any number in the middle between those. What number could I pick between -2 and 1? You could do -1 too. Either one. Doesn't matter. Live your best life. None of those are going to be open circle. All of those are going to be closed because of the or equal to. What point do I need to include with my third rule? 1. Is that going to be an open circle or a closed circle? Open. So make those notes, okay? Make those notes on which points were going to be open circles. When you're doing a transition, on one of the lines at the transition, you have to have an open circle. All right? You need to make note of that. Now that we have this, I need values greater than 1. 2 and 3. Okay? So let's go ahead and evaluate our function. So f of x equals -4. So f of -2 equals -4. There's no x value to plug in. So my ordered pair is just -2, -4. What about for x equals -3? -3, -4. Because this says, does not matter what your x value is, y is -4. F of x will always equal -4 for that section of your piecewise. So, -4, -4 is another point. What type of line is this? If I just have -4, -4, -4, -4, -4, horizontal. Okay, remember that's what a constant function is. It's a horizontal line. Y is always the same thing. Now we're going into our linear equation. So if I have f of -2, what is f of x? Say that again. Yep. Okay. F of 0. And f of 1. You could if you wanted to. We just picked a point that was between -2 and 1. We had to include -2. We have to include 1 because those are the transition points. And then just another number between them.
So could you do like -2, -1?
You have to have 1. So if you did -2, -1, 0, you have to do another one for 1. Okay, you have to include both of those. Okay. And then we get 1. All right, so my third rule, f of x, x squared. So what's f of 1 going to be? What's f of 2 going to be? What's f of 3 going to be? Okay, so I've got this point. And again, we said this one needs to be an open circle here. And this one needs to be an open circle as well. But I also want you to notice something. Oops, this one. Yeah. They overlap. Sometimes that happens. So then I don't have to worry about the fact of open and closed. They end up meeting. Now the rule will change, so the shape will change, but where one ends, the other one will begin. Now we have a gap between the first and second rule, but our second and third rule end up overlapping, so the transition's a lot smoother. So let's graph these. So my first rule was -2, -4, -3, -3 what? -4, yeah, they're all -4, there we go, that's right. Because that's our constant function. So I have my points, -2, -4, -3, -4, oopsies. Remember that one needed to be an open circle at -2. -2 has to have that open circle because it's less than. X is less than -4. Or -2, sorry, -2. X is less than -2. Then our next one, we've got -2, -5. Then we had 0, negative 1, and 1, comma 1, right? That was our second rule. And again, we know it's a linear function, so I've got 2, negative 5. Everything was a closed circle. 0, negative 1. It would help if I put that in the right spot. There we go. Boom. So it only goes from negative 2 to 1. It stops. Okay? And then I go into my third rule. My third rule was what type of equation again? Parabola. So remember, I'm going to have that U shape. Okay? So it's not going to be a straight line. It's going to be a curve. So we kind of need to look and see the point and try and fill it in as a curve. So I had 1, 1. Okay? And remember, that was supposed to be an open circle, but 1, 1's already point, so they just kind of overlap, so it's not really a big deal. Then I had 2, 4. And then I have 3, 9. Which is way up here on my graph. Way up there. Okay? So I see that that's not a straight line. So it ends up curving. And so now we see that transition. Instead of it being a straight line, now it's a curve. So it bends. You need to be aware of that. And then here, there's my 3 pieces. I have to start linear equation in the middle and then a parabola at the end. Let's talk about domain and range. You still need to be aware of those. Okay? Domain represents all of my what? X values. So looking at this graph, I've got my X values continuing left forever. And then I go, and I jump down here, and I go up, 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 and I'm going up and to the right forever. So what's my domain going to be? Negative infinity to positive infinity. Good. All real numbers. Range is all my Y values. What's the lowest Y value that I have in this piecewise function? Negative 5. Okay, because this doesn't go down at all. This just goes straight across to the left. It doesn't drop any lower. This stops here. So it stops at negative 5, and then it picks up, and then it goes up, 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 up forever to infinity. So when you're looking at your piecewise functions, you need to be a little more careful with the domain and range and looking at how the different pieces interact with each other and which ones continue to go to the left forever, go to the right forever, going up or down, where does it start, where does it stop? Because different functions will have wildly different domains and ranges. Depending on where the domains cut off. Okay, so looking at those, you're going to have to take a little bit more time and care thinking about what the domain and range of a piecewise function is going to be. It's less predictable than our non-piecewise functions. Yeah.
How does domain go?
So, because it's going up and to the right, it's never going to be a straight line because it's not a function anymore. So, even though it's going up faster than it is going right, it's still going right forever. There's nothing to stop it. Alright, so these are some of our common graphs. 3 of these you've already seen. 1 of those you may not have before. Okay? My linear function, f of x equals x. This is my straight line. Okay? Linear functions. Quadratics with the U shape. Absolute value with the V shape. And then we've got square root, which is half of a parabola. Okay? Turn sideways. Absolute value. So these are common graphs that you'll see on, you can see them on piecewise functions. You'll also see them as we move into transformations. Okay? So transformations is taking a graph and moving it. So our first 2 types of transformations, we have a vertical shift and we have a horizontal shift. And looking at the equation tells us what that shift is going to be. Okay? Vertical shift means that we take our function and we add or we subtract something. Okay? If I add a value to my function, say I have y equals, let's do it in function notation. I have f of x equals x squared. If I add something to it, then it takes that function and moves it up. If I subtract something from it, it takes everything in that function and shifts it down. Horizontal shifts are movement left and right, and that's taking the x value and it's adding or subtracting something. So how it's going to look different, I still have x squared, But instead of me adding something to x squared, I'm actually subtracting or adding something to x before it gets squared. Okay? The big difference is you'll see a grouping symbol or not a grouping symbol. So vertical shifts are something that happens outside of groupings, while a horizontal shift is something that happens inside of a grouping symbol. Okay? Grouping symbols being parentheses, absolute value, even a square root symbol, anything that's all underneath the same square root symbol, that's still considered a grouping symbol. So if I had the square root of x minus a number, that's going to take my square root graph and it's going to move it to the right. Yeah. Now, what's important to note with your horizontal shifts, vertical shifts make sense. Add a number, go up. Subtract a number, go down. Horizontal shifts are going to be backwards. Because as we see, if I'm subtracting a number, I'm moving to the right. So I have x minus something, it moves me to the right. X plus something moves it to the left. And what that basically has to do with is I have to kind of shift my function to end up in the same y value. So I need to move left or right to counteract that. Okay? So just note, when you have a horizontal shift, it's going to be opposite. You'll see that as we get into more complicated transformations at the end of the year. We start doing stretches and compressions and things like that. Anything inside that grouping has kind of this backwards opposite effect because we're doing it to x before we have the chance to change the function. So plus moves to the left, minus moves to the right, plus moves up, minus moves down. So we're going to graph our function. X squared is considered our parent function. It's MATLAB. This is our parent function. Okay? Every single quadratic function, if there is an x squared, and then it's some other stuff, every single quadratic function looks like this. This is kind of the parent, and then everything else is like the baby functions. Okay? Everything is modeled off of this U shape. And so no matter how complex my quadratic equation ends up looking, okay, I could have negative 3x plus 2 squared. Actually, let's even go crazier. 1/4 x plus 2 squared minus 7. That quadratic is modeled after that shape. So no matter how complex it gets, it's still modeled after the same shape. It's just going to move, and it's going to get wider or smaller. It's going to flip upside down or left or right. So it's just going to change based off of our parent function. Okay? So when we're looking at f of x as our parent function, and then g of x is our parent function minus 3. It's my parent function minus 3. So g of x is f of x minus 3. Well, when I have f of x minus a number, how does that move my graph? Down. And it's going to go down that number of units. There we go. Okay? So we're going to go down 3 units. It's going to take all of those points and it's going to shift them down 3 units. So I have the point over here. I've got negative 2, 4. If I move it down 3 units, it's now at negative 2, 1. 4 minus 3 is 1. If I take the point negative 1, 1, it's going to shift down to negative 1, negative 2. 0, 0, 0, negative 3.
What does that word there makes me shift the original graph?
Down. So 1, 2, 3 units down. 1, 2, 3 units down. Everything's moving down 3 units. And then I have my new graph. That's g of x. It's my new graph. Everything shifted. All the y values were decreased by 3.
Slide 64.
Alright? Different change. Different function, different change. I want to try to finish up and I'll go back. So I have an absolute value. Okay, it gives me that V shape. So my parent function is f of x equals absolute value of x, and now I'm transforming it into g of x is the absolute value of x plus 2. So now that's inside of my grouping. So g of x is f of x plus 2. I took my inside and I'm adding 2 to x. Okay? It's inside my grouping. So it's going to be a horizontal change. So when I'm adding something inside my grouping, which way do I move? Left. Moving to the left. Okay? So this means I'm going to go left 2 units. Take all those points and move them left 2 units. Going to put me units to the left, 2 units to the left, 2 units to the left. Boom, boom, boom. There's my new graph. Everything's just 2 units to the left. So that horizontal change has that backwards kind of behavior. Every time we have a horizontal change, it's a very backwards kind of behavior. So you just need to have this note in your head that when you see a horizontal change, it's going to be opposite of what you would normally expect. Adding moves me to the left. Subtracting moves me to the right. It's backwards. All of those points, so 0, 0, became negative 2, 0.
So when it's absolute value, it's being left of this.
No, the grouping is just telling you the parent function. The movement is where that addition or subtraction is taking place. If it's inside of a grouping symbol, absolute value, parentheses, a square root, that means left or right. If it's outside of the grouping symbol, that tells you up or down. Now, last one is reflections. In this last example, we're actually going to include all 3. You don't have to have just one transformation. You could have 2 or 3 or 4 or 5. Depends on what the equation is. So we're going to have up to 3 because we have horizontal shift, we have vertical shift, and now we're adding in reflection. Reflection takes the graph and turns it upside down. Okay? Takes it upside down. It reflects it over the x-axis. There's also such thing as a y-axis reflection, but we're not going to be doing those right now. We're just going to stick with the x-axis. So we're reflecting it over the x-axis. So this function has 3 transformations. It's got a vertical shift, it has a horizontal shift, and it has a reflection. The negative in front tells me to reflect. The plus 2 tells me to move which way? To the left, because that's my horizontal change. And the minus 1 tells me to go where? Down. Okay? Now, the order that you do these is important. Okay? This is the easiest order that I've found. Do your horizontal change first. So let's go left 2 units. That's inside of our grouping symbol. We always do parentheses and grouping symbols first anyway, so you can think about your order of operations. We do our grouping symbols first. Okay? Everything inside our grouping symbol we're going to do first. So we're going to move left 2 units. Okay? And then what we have left is our reflection or our shift. Well, multiplication happens before subtraction. So we're going to do our reflection second, and then we're going to end with our vertical shift. Okay, so grouping symbols first, multiplication second, subtraction last. So we're going to do those shifts in that order. We're going to start by going left 2 units. Take all these points and go left 2 units. Okay? I'm not going to draw the full line because I'm not done yet. I just want to show where that first shift is happening. We're going left 2 units. Then we're going to reflect it. Reflect it means to turn it upside down. So any y values that were positive are now going to be negative. Any y values that were negative are going to be positive. We're going to flip it. So if I had the point -3, 1, well, now it's going to become -3, -1. I'm going to change the sign on that y value. And that's going to be the same for -1, 1 is going to become -1, -1. 0 is just 0. Okay, that point there. All right, so I just flipped it upside down. The green line, flipped it upside down to the purple line. Now I can end with my vertical shift, down 1 unit. So everything is going to come down, down 1 unit. And that is my final graph. Everything moves down 1 unit. All right? That's all 3 transformations combined into one beautiful, lovely graph. That's as complex as it will get for now. Till fourth quarter. Fourth quarter, once we're done doing a lot of quadratic stuff, we'll do more transformations. But for now, we're going to leave with just those 3. Okay? So you do have